So before we dive into the technical details, here is a very high-level overview of AI research. So there are two sets of tasks. There are sets of tasks where humans can do, and there are things that AI systems can do. For many of the existing NLP research, what we typically do is we take the tasks that humans can already do, and then we train AI systems to automate human effort. So, for example, humans can do sentiment classification well, humans can label news articles into different categories, humans can detect spams, or extract shallow information from the document. For all of these tasks, we collect human labels, we treat the human labels as ground truths, and we optimize the AI systems to mimic human labels, and we evaluate the AI systems by checking whether they agree with human labels. This is a standard supervised learning framework. However, if we are only focusing on things that humans can already do very well, we are missing a lot of opportunities. Because for many things that humans actually care about, humans actually struggle to determine the ground truth. So for example, humans might not be good at analyzing large corpus, humans might not be good at writing complex programs, humans might be bad at brainstorming new hypotheses. And it would be great if we can augment human capabilities and ask AI to help us with things that we struggle to determine the ground truth and achieve what we could not have achieved before. However, there is a question, which is how do we supervise AI systems to do those tasks? If humans might not be good at those tasks, then human labels will be very suboptimal. One way to do this might be reinforcement learning, where you provide AI systems reward function and then ask it to optimize it. However, in many cases, we even struggle to determine the best reliable reward function. Then the focus of today's topic is how do we supervise AI systems even when we struggle to determine the ground truth. I will ground this discussion into two concrete applications. First of all, an application where we translate a natural language question into a very complex SQL program where an expert can make mistakes. And in particular, we are focusing on the cases where how we can enable people who do not understand SQL programs to label SQL programs, which will be used to train an AI system. And for the second case, we're going to feed an AI system to a large group of text, and then we're going to ask the AI system to describe their difference between the two corpus. And this is also a pretty hard task because humans have to look at large walls of text to decide what is a good description. So these are the two tasks that I'm going to talk about, and here is the overarching framework that I'm going to propose, which I call it label, verify, reduce. First of all, it is clear that the standard supervised learning framework will not be viable here because labeling those data will be pretty hard for humans. So instead, perhaps it's much easier to reduce this problem to asking human to verify which one of the AI systems output is correct. One analogy of this could be P versus NP, where there are a lot of computationally challenging problems that are NP complete. However, if someone gives me a solution, I can pretty easily check that it is correct. The same philosophy can be applied here. AI can propose several different candidates, and all humans need to do is to verify that the candidate answer, which one of the candidate answer provided by AI system is correct. The AI system can be trained in any way. So for example, it can be done by feature prompting, reinforcement learning, unsupervised learning, whatever. All human needs to do is to verify, because verify is much easier. So it looks like we have solved a lot of problems here, but not really, because in many cases, verification is still hard. For example, if you ask someone else to write you a program, then how do you verify that the program is correct? If someone tells you that two corpus have the difference is a certain natural language description, how do you tell that the description is faithful? But it's still hard, so we propose to further reduce this verification problem to something simpler. So for example, instead of verifying which program is correct, we can verify whether the program is correct on simple to understand test cases, like the input-output examples. Instead of verifying a distributional property, you can decompose the problem to verifying the property on individual samples. And then perhaps after you get the results of individual samples, you can later combine them together across the entire distribution. So this is the overall framework. And now I'm going to apply this label verify reduce framework to the application. And the first application that I'm going to talk about is to enable people who do not understand SQL programs to be able to indirectly label complex programs that even at first can make mistakes. So here's the standard semantic parsing task, where you have the natural language question, how old is the youngest person from department A, and then you're trying to have an AI system that translates this into a SQL program. In this case, it's pretty simple, so like minimum age from people where department equals A. And let's assume that in this setting, we only care about whether the SQL program is correct. If you want to train such a system, if you want to supervise an AI system to do this, the SQL program can be pretty expensive to annotate because you have to hire people who understand SQL programming. Sometimes they need to have a computer science degree in order to do it in an effective way. And the research question here is, how do we enable people who do not understand SQL, which we call non-experts, to label these programs for the given natural language question in order to train an AI system? Remember the first part of our framework, converting the problem of labeling the full output to verifying which one of them is correct. So let's say we have codex, which will be translating the natural language question on the top to several different SQL candidates, which are different, and each of them are given a probability score about the codex confidence. And suppose that we have this short list of SQL programs, and suppose that we are having the list to be long enough such that the correct candidate is in one of them, then the problem simplifies to how do we enable people who do not understand SQL program to verify which one of the candidate is correct. So you might say, okay, this is a pretty easy task because in the natural language, youngest person corresponds to minimal age, and department A corresponds to where department equals A. So you probably don't really need to understand SQL at all to easily identify which one of the candidates is correct. However, I picked this particular example to be simple such that people can understand the task, whereas the average case example looks like this. You have the question, find the first name of students who have both cat and dog hats, and then the model would generate several gigantic SQL programs, and it's very challenging for me who actually understand some SQL to tell which one of them is correct. And what makes the matter worse is that we are going to ask people who do not understand SQL to tell which one of them is correct among 16 different such candidates. This is challenging, and I will tell you that one of the SQL program is wrong later, but all you need to know here is that this is a challenging task, and secondly, both of them will deliver the right answer in most of the times. However, one is more robust when multiple persons have the same first name. All right, anyways, forget about this hard example. Let's look at how we can further reduce this problem to something simpler that some people who do not understand SQL can provide meaningful supervision signal. So let's say we have the natural language question, how old is the youngest person from department A, and 3 candidate SQL program. Let's say we have, magically speaking, like some database that comes out of nowhere, and suppose that we have this database. Then what we can do is we can ask people who do not understand SQL program to say, what is the answer of this question on this database? And the people who do not understand SQL will be able to say 23. And then we can execute all of the 3 SQL programs on this database, and 2 of them give us the wrong answer, 1 of them give us the correct answer. As a result, we can tell that the last SQL program is correct. So in other words, the people who do not understand SQL, the non-experts, will only see the database and the question, and they will produce an answer. And by producing the answer, they can rule out the SQL programs that is not shown to them.
So is this, you're only using like really small databases that people can expect?
Yeah, exactly. I will talk about it later. You predicted my next slides. Cool. Okay. So there has been actually a large literature on how to use these like execution signals to supervise semantic parsers. But like difference here is that we actually have the choice to choose one database to present to the non-expert annotators. And one philosophy here is that we need to choose the database wisely in order to make the replication simpler for the non-experts. So here are two criteria. First of all, the database needs to be small enough to comprehend, as you have predicted. And secondly, it will have to make different programs return different values as much as possible. For the first one, so in principle, we can provide the non-experts a 1,000 row database, and then they can provide an answer on this, probably by looking through the database for an hour. However, this is not very effective. So we say that the database needs to be simple to comprehend. And we formalize this saying that the size of the database needs to be smaller than a particular value. And the size is determined by the number of rows in the database. And remember, size will be a function that maps from a database to a real number. So here is a pretty small database. However, this database is not useful either. Because suppose that we ask the non-experts what is the answer on this database, the expert will say 23. But all of our SQL candidates might also say 23. So in that way, we actually get zero information out of which one of the SQL program is more likely to be correct. And we are simply wasting the annotator's time if we present such a database. So we say that this is not informative, and we quantify this using the expected information gain criteria. So let's say Codex produced 3 SQL programs, and then each of them, for simplicity, has a probability of 1/3. 2 of them returns a value of 23, 1 of them returns a value of 26 on this particular database that we provided. And then to calculate the expected information gain of this database, it is the same as calculating the entropy of the answer. And we calculate the entropy of the answer by first grouping all of the SQL programs that return the same value, and then add the probability together, group them, and then calculate the answer entropy. And in this case, it's 0.92 bit. To formalize this, we say that the database, the information gain of this database is going to be 0.92 bit. And the information gain function is a function that maps from the database to a real value as well. So now we have defined the 2 criteria, and then all we need to do is to search for a desirable database I that has a small size I and a large information gain. So because of time limit, I won't be able to talk about the technical details, but what we did there is we first used fuzzing to generate a large number of random databases, and those databases are probably also pretty large, such that some of them will have very high information gain. And then we greedily drop the rows from that large information gain large table, such that the information gain will still be approximately the same, while its size is gradually reduced. We also did multiple rounds of interaction, just in case one single database will not be able to roll out all of the other incorrect SQL programs. And finally, there's no finally. Okay. So we also have some ongoing work which tries to learn a neural network that tries to directly predict a small and informative database condition on a list of SQL programs.
So one clarifying question there was,
Sure.
so the information gain is defined with respect to like already generated candidates,
Yes,
right?
yeah, exactly.
Yeah, so at the time when you're deciding which database to use, you kind of know the model candidates, is that correct?
Yeah, exactly. So we are actually searching, good catch. So we are searching for the database with respect to all the SQL programs. Okay. Well, all right. So here's a human study setup. Because we motivated this project by asking non-experts to annotate SQL programs. So we recruited 11 Berkeley students, they're non-CS majors, and we make sure that they have 0 SQL experience. And we also, like just a spoiler, the best annotator was actually an art history major who has only used Excel before. And in order to complete this task, we collect a lot of human labels, and they only need to answer on average 4 database questions with 9 rows per question. And here is the data set that we use, and here is a baseline. So there is a national language question, how old is the average person from department A? And this question is coming from the spider data set, where each question is annotated by a database expert who knows how to write SQL program. And it is shown in orange. Right now, we treat the orange one as the ground truth. And you might wonder, okay, am I supposed to be talking about things that humans might struggle to do? And why am I using human experts annotation as a ground truth? Let's first assume this for simplicity right now, and then I will come back to this assumption very quickly. So let's say the orange one is the ground truth. And now we're going to test our framework by asking people who do not understand SQL program and then compare it to the expert annotation. So remember our pipeline. So first of all, we ask Codex to generate several SQL programs. So the Codex will predict different SQL programs. They are sorted by probability scores, and we label the most confident program as the purple one here. And we say that this is the top Codex top one accuracy. And then we compare the purple program to the orange program by approximating the semantic equivalence on a large set of databases. So this is like the purple is capturing the baseline where we simply trust the most confident outcome from the AI system. And then we can provide the non-expert the database, and the non-expert will provide us some answer. As a result, we can rule out some of the incorrect SQL programs. And at the end, we have some SQL program which is being left. And we call this blue one to be our own annotation. And we compare our own annotation with the orange gold standard. So the victory condition here is that after we interact with the people who do not understand SQL program, the blue accuracy should be higher than the purple accuracy. And in the other way of saying this, it means that suppose that we interact with people who do not understand SQL, it should outperform the baseline of simply trusting the most confident answer from an AI system. Cool. So let's see the result. First of all, the orange one represents the original expert SQL accuracy. And because we are using the original labels as a ground truth, by definition, it is 100% accuracy. Codex is 72% accuracy if we simply blindly trust its most confident outcome. And very unfortunately, after we interact with people who do not understand SQL, the accuracy drops by 3%. This means that if we interact with the non-expert, we actually could have been better off if we just ignore their advice and then trust the Codex top one accuracy. So this seems extremely worrying at the beginning because we spend a lot of effort and it doesn't really work. And then so we dug into the details about like what are the places where non-expert made mistakes. And it turns out that the annotation quality was pretty reasonable. And the reason that we observed this performance drop is because we use the original expert labels as a ground truth. So you might wonder, what are the places where they make mistake? So here is the place where they made a subtle mistake. And this is an example that I've shown you before. Find the first name of students who have both cat and dog cats, and the expert wrote the red SQL program. What the red SQL program do essentially is they will first find the first name of the student who have cat, find the first name of the student who have dog, and then take the intersection of the first name. Usually it will give you the correct answer. However, if you look at this particular database, it is very obvious that the red SQL is wrong. So here you have two students. You have Alex Wei and Alex Pen. One of them has a cat, one of them has a dog. Suppose that you follow the logic of the React SQL program, they will say that, oh, there will be a student who has the first name of Alex having a cat. And there is also another Alex who has a dog. Therefore, there is an Alex that has both cat and dog, which is actually a wrong answer because there is no student who has both cat and dog. So given that there were a lot of annotation mistakes by the original expert, we decided to use our framework to re-annotate the data set. And in particular, we want to prevent ourselves from biasing against the original annotation. So what we did is we stick to the original label if we find the natural language question to be ambiguous. Secondly, we only fix the uncontroversially words labels. So there are two authors who are going to be doing the relabeling, and we only fix the original label when we unanimously agree and can come up with a strong reason that our new label is better. We also talked to the first author of the original Spider dataset, and they supported our re-annotation decisions. Okay, so after re-annotation, here are the results. We find that the original expert accuracy is definitely not 100%. It's actually only 75%. The codex top one accuracy is also dropping, which is 59%. And the reason that it is dropping is because codex is mimicking the wrong expert demonstration in the context. And our non-expert annotation can improve over the codex top one accuracy by 16% significantly, and it matches the performance of original expert, which did not use our system. Go ahead.
You say the codex top one accuracy decreases because of the kind of mislabeled examples in the context.
Right, yes.
Did you like try replacing those?
We haven't tried, but this is probably one thing that we probably should do. Yeah. All right, so to recap this section, writing complex programs is a very hard task. So we first convert the problem of labeling the program to verifying which one of the program, which might be simpler for people who do not understand SQL, but still it's hard. So we convert the problem of verifying which program is correct to verifying which program is which input-output behavior is correct. And finally, we reduce the cost of supervision by making verification simpler and effective by choosing the databases wisely. All right, so I'm going to move on to the second application, which is describing the differences between text distributions using natural language. This is a fairly new task, so let me describe the setup. You have two large groups of text, and they are coming from two distributions, D1 and D2. And here you want to describe the difference in natural language. And one way to describe them is D1 contains more French sentences compared to D2. Sometimes there might be multiple different natural language descriptions. So it could be D1 contains more accent marks compared to D2. Both of them are correct as long as it is able to tell apart these two corpus. So that was a pretty simple example. That this is the usual case that people might need to struggle with. And it is a pretty hard task, and I don't imagine people to be able to solve it very quickly unless you have either seen the answer before or give me an answer that the difference between these two corpus is that one of them is in brown and one of them is in green. But anyways, in this case, if you look at the individual sentences and compare them, D1 mentions more female entities compared to D2. So why do you even care about such a task? Well, it turns out that a lot of important applications can be reduced to this task. For example, suppose that you have a distribution shift. You can feed the test distribution and the training distribution to our system, and our system might be able to say the test distribution involves more formal writing. Suppose that we want to understand a large corpus. You can first run text clusters, but each text cluster could be hard to understand. So you can feed the text clusters to our system, and our system can say, one text cluster contains more sports-related articles. You can also do some social science studies where we can feed the public opinions from this year and feed the public opinions from last year, and trying to ask our system to describe the difference. And our system might say the public opinions from this year are more optimistic about the pandemic. And the list will go on, and there are a lot of different applications for that. However, this is a hard task for human. So how do we supervise it? Remember the first part of our framework, which is converting the problem of labeling the full outcome to something that is easy to verify which one of the output is correct. So translating it to a concrete algorithm, we will have one system that can propose different descriptions of how two distributions are different. And we do this by GPT-3. We prompt GPT-3 in the following way. We have 4 sentences from group A, which is from distribution 1. We have 4 sentences from group B, which is from distribution 2. And then we say, compare 2 sentences from group B, each sentence from group A, underline, and let GPT-3 complete the sentence. And GPT-3 might be able to come up with different descriptions. So for example, is more positive, which is actually correct in this case. And sometimes it is just ranting. So for example, it says it's more offensive in tone, and there could be also other descriptions as well. But don't worry about the noisy descriptions, because later we'll have people or other AI systems to verify that they're wrong. And now let's come to the bigger picture. The second part is, how do we verify whether a description is correct? And still, it could be challenging, because you can imagine that in order to verify whether a description is correct, you'll have to look at the description and look at the entire 2 corpus, which can take some time. And it will be very hard for you to do it at once. So what you could do there is to reduce the problem of verifying a distributional property to verifying the property on individual samples. So we say that a good description will help humans tell individual samples from D1 and D2 apart. And specifically, we operationalize it in this way. Let's say there is a description. Samples from D1 are more positive than those from D2. And to evaluate its quality, let's say we have 2 samples from 2 distributions. However, we don't know whether DA is from distribution 1 or DB is distribution 1. We are going to have 2 samples, and then we are going to give it to human. Oh, by the way, this is the second author of the paper. We are going to give it to human, and then the human will use the natural language description to tell which one of the A or B is distribution 1 or distribution 2. And suppose that your natural language description is good enough, then it can help human classify whether XA is coming from D1 or XA is coming from D2. So in this case, after seeing this description, the human could say, I think XA is from D1 and XB is from D2. That is just for one pair of samples coming from D1 and D2. We can repeat this for 100 times. And then we calculate the human classification error rate using that natural language description. So another way to say this, the quality of a natural language description is decided by how well it can enable another human to tell the samples from these 2 distributions apart. Another way to look at this is we are trying to learn a natural language hypothesis. In the classical settings, we try to find the most discriminative linear weight. It is going to decide a hyperplane, and it can separate the input vectors into 2 classes. And in our case, we try to find the most discriminative natural language string, and the decision boundary is given by, we give the natural language string to another human, that human will look at that string and decide the decision boundary, and then try to separate the input vectors. So it looks like we have reduced the problem to some verifiable form. However, it is very expensive to actually have human verify that, because you have to have a human sit down, look at the samples from 2 corpus, and then actually, when we try to use that evaluation framework in our paper, if for describing text clusters, it actually costs us $10 to evaluate the quality of each single description. This is not very economically feasible. So what we did here is we're going to have another machine learning model to mimic the human classification process. So we use a question answering model, unified QA, and then we ask the question answering model, is XA more positive than XB? And then the model will say yes or no, and then we can calculate the error rate of the model trying to classify the samples from these two distributions, and then use that to approximate the human classification error rate. So to take a step back, here is the method overview. We first use GPT-3 to propose 60 different descriptions of how two distributions can be different. And next, we're going to verify whether each description is correct with a machine learning model on individual samples from the two distributions. There are also some method we propose to create the fine-tuning data for GPT-3, and you can check out the detail in our paper. Cool, let's look at the results. And here's the benchmarks that we used. So some of my previous work gathered 54 different text classification data sets. And each of the text classification tasks is annotated with a natural language description. We will feed the positive class samples and the negative class samples to our system, and our system will try to recover the description for the positive class. And suppose that description is consistent with our language description about the classification task, then we say that the model successfully recovers the underlying description. Here's the result, and there's nothing very surprising here. Suppose that we use GPT-3, the performance is only 7%. Suppose that we use GPT-3 plus the machine learning verifier, it's 31%. Suppose that we add additional fine-tuning, it's further increasing. And suppose that we use a larger model, it just like increasing as expected.
Is that a larger model plus all the other things?
Yeah, larger model plus all the other things, and also we are only using a larger proposer, and the verifier is still the same. Okay, cool. All right, so you might wonder, okay, so are the expert annotation actually always correct? And it turns out that sometimes it's still pretty noisy, and the error was actually indeed out of my own expectation. So there's a data set called SUBJ. It's called Subjectivity Analysis Dataset. At least 4 different previous papers on few-shot learning uses that paper to classify the sentences into subjective class and objective class. And my paper belongs to one of them. We feed the positive samples and the negative samples to our system. Our system generates the objective class is a plus summary of the film. And we were super confused because it's basically sort of orthogonal to subjective versus objective. It turns out that if we dig deeper into the original SUBJ dataset paper, it says to gather subjective sentences, we collected 5,000 movie review snippets. And to obtain objective data, we took 5,000 plus summaries. And we actually contacted other 3 papers who used the dataset in this way, and none of them actually know that the dataset was collected this way. And this dataset was just sort of propagated and being used by more papers without actually knowing that about how the dataset was originally constructed. So let's look at the concrete application of why this system could be useful. So we can use this system to find spurious correlations. The motivation here is that machine learning models sometimes can pick up shallow correlations, which is undesirable. And we focus on the spam classification dataset that has more than hundreds of citations. Let's say the spam class is distribution 1 and non-spam is distribution 2. We feed the positive class and the negative class to our system. Our system first says D1 contains more spam. Okay, that's pretty much expected because that's a spam classification data set. But our system also says D1 contains more hyperlinks. This is slightly unexpected, so we investigate further whether there is a sparse correlation or dataset shortcut on this dataset. And it turns out that if you fine-tune a Roberta model on this model, on this dataset, it will always predict spam whenever it sees a hyperlink. So I took all of my Slack message sent to the second author of this paper that contains a hyperlink. Every time this classifier will say that it's a spam. However, if we remove that hyperlink, it will say that it is not a spam. And finally, I want to make it a caveat that our system is also used to inform the human decision maker. So, for example, in some cases, human developers might indeed say that we do want to use whether it looks like plot or reviewed as a feature to classify whether it's subjective versus objective. And in some cases, we do want to use spam as a very salient feature to, hyperlink as a very salient feature to classify spams. However, we would argue that if they indeed want to use their features as that in these ways, they should at least know that. And our system can keep them aware about these artifacts of these data sets. So to recap this part of the talk, labeling the descriptions of how two corpus can be hard. Between two corpus can be hard, and we convert this problem to verifying which description is correct. And further, verifying the distributional property can still be challenging, so we reduce it to verifying the property on individual samples. Finally, we can make verification cheaper by simulating human verification with a machine learning model. All right, so that's the concrete part of the talk, and now I'm going to talk about future work and discussion. A very high-level question: what can AI do? We used, at least what I used to think is like what a human can do. So, for example, we can ask AI system to mimic humans. However, there's probably more to that because we know that P is not NP, and perhaps we can make it more complicated by asking AI to do things that one human can verify. However, this is still not the right upper bound because what one single human can verify without any tool use is actually still pretty limited, and we can go much more beyond that. So we can further improve the boundary to what a large group of humans can verify with the help of AI and other tools. So that seems to be a much higher upper bound than what a single human can do themselves. And there will be a lot of opportunities for augmentative AI systems. So for example, machines can be particularly good at search, and after machine learning has done the search, humans only need to verify. This means that machines could be potentially better at creativity because it can sample a lot of output content and search for the most creative one. It can also search for effective strategies to do a certain task or communicate with humans. Humans might not be good at distributional properties because when humans look at a large number of data, humans usually have a biased impression. And low battery.
Oh, you can connect it.
Or I can finish it fast. And this is a place where machines can help because machines can do statistics in a relatively unbiased way. And finally, machines can be better at non-input things because we humans only have a small brain while computers have a large memory. And machines can potentially be better at long-form summarization and long document generation. However, there are going to be a lot of challenges as well. First of all, it is hard to create training data. In our framework, we proposed the label, verify, reduce setup where we can indirectly supervise an AI system. However, that framework still has a lot of limitations. So one limitation could be that what if the AI system proposed candidate does not actually contain a correct candidate? So that is very worrying. However, in the future, we might expect AI system to be better edges because AI's capability seems to be increasing, and hopefully one of the top K elements is going to be correct. And secondly, what if humans cannot even directly verify? So suppose that the task is super hard. Perhaps humans is just fundamentally incapable of understanding what the AI is doing and whether it is doing things correctly. And certainly verification is probably going to be harder and harder because humans are going to be applying AI systems to more and more complex tasks. And for many more complex tasks, they're open-ended, and in many cases, there are no single correct answer, and evaluating their behavior is going to be challenging. And finally, I want to talk about a problem with benchmarking, which will be a problem if we want to incentivize more people to work on this field. So in the case for automation in the past, what it usually looks like is I spent $2K on AMT and I spent $2,000 on 20,000 data points. I can tell that the labels are correct by scrutinizing some annotations. But right now, perhaps in the future, I spend $2K on experts to label 54 data points. The labels look reasonable, but I'm uncertain whether they are correct or not. But this will be a challenge, and here is my personal adaptation strategy, which is, first of all, instead of thinking that ground truth is given and always observable, right now you might need to think about ground truth as some hidden variable. You can collect indirect evidence that it is correct, but you might never be able to observe it. So you have to be more Bayesian when you interpret the performance metrics. And in particular, your interpretation will depend on how confident are you in the existing human labels and how confident are you in the existing AI's capability. So for example, suppose that you have a bunch of very high confidence labels that you know that they're absolutely correct, and you know that the current AI system that you're testing against is not very capable, then you can roll out these systems pretty quickly. However, suppose that you have low confidence in those labels, then probably you might want to collaborate as like calling experts to collaborate with these capable systems in order to improve those low confidence labels. Okay, so that's going to be the end of the main part of the talk, and here are the main takeaways if you can only remember 3 things from this talk. First of all, we can indeed supervise AI even if we struggle to determine the ground truth. Secondly, we propose a framework of converting the problem of labeling to verification and reducing it to some simpler verification problem for non-experts or humans in general. And finally, augmentative AI system is a vastly underexplored research area with a lot of opportunities and challenges. And unrelated to the talk here, my other research threads, if you're interested in talking to me or about it later. So I work on prompting, which is a pretty popular hot topic these days. And arguably, I implemented the first version of instruction tuning 6 months ahead of Hugging Face and Google, and I actually predicted their success. And we also have some recent work on learning from natural language explanations. I'm also interested in program synthesis, and my research agenda there is to bridge the gap between surface form synthesis method and execution semantics. And finally, I'm interested in building statistical models of how models learn. And in particular, I want to build theories that have strong predictive power about how neural network would empirically behave. Okay, so that's the end of the talk, and I'll be happy to take questions and discuss.
So